write it down. Try to explain that as best you can.
I took a class like this about all this stuff that was called Science and Technology.
Oh, nice.
That talked about all these like claims and why they work. I mean, it wasn't like physics oriented though. It just talked about things.
I want to know the physics.
So what kind of physics?
It just pushes the air down.
You just say the name of it, or
I don't know. It's just like, you know how like it starts like slanting. Like how does it not like
how
go
do you
over?
answer that? Like how would you answer that?
You know what I mean?
I'll let you know how I'd answer it.
It's like there's
when
no
you guys,
no,
after
because
you guys
it's like,
push it
answer.
out,
you
it's
just say
like
the
at an
name of
angle.
it, or
Well, no, I kind of explained like why you think you know the name of it,
What?
but
Shouts out
why
to
you
my
think that
homie
would
Ray.
allow her to pick up something heavy.
I got that. Already got it.
Alright.
You know what?
Wanna get started on your warm-ups?
I need my time.
World Star. Gonna get started on your warm-ups.
You're not really sorry, Crispy.
I'm here too.
Chris, where you going?
He's going to
Okay, let me know
McDonald's.
before you go.
He's going to McDonald's.
He's gonna run.
Get started on your warm-ups.
looking? No.
I didn't say a word. I left my back there.
Is this the same like the video we watched about the man that was thinking like the weight?
I mean, yeah, that is similar, but that's because of torque. This is because something slightly different.
Alright.
Yeah.
I don't even know.
We turn off those.
I don't know. I wonder what the word.
Yeah? I don't know. I just get like, I don't know.
We're starting on the warm-up. What's the thing? Levery?
Leverage?
Yeah.
Right now.
Uh-huh.
All they've done is not harass. I've been harassed by Swoosh.
Okay, so what do we think? What's going on here?
Because of the pulley, it redistributes the like weight. There's leverage.
And also,
So it has to do with wait, hold on a second. So it has to do with the pulley. Okay.
The
It's
pulley.
what someone else saying?
it bears the weight, so it bears more weight.
Pulley is bearing weight.
It's like leverage. It redistributes the weight.
Okay. Gives the girl
Strength.
leverage.
And mass.
Okay. Cool. Anything else?
Other than that, it's
Could
just
where
like
she
really
pulls
buff.
on the string affect?
Yeah.
She can move it?
If she pulled it higher, wouldn't she pull lower the weight?
Yeah, so it has to do with, that might have to do with leverage. If it's kind of awkward pulling on the rope, that might make it more difficult for her. Obviously, she needs a good enough grip.
Obviously, she should not be wearing sandals.
Yeah, that's true. Well, we're gonna talk about a pulley and other what are called machines, simple machines. We're gonna talk about these other machines that allow us to do things we wouldn't normally be able to do. So you wouldn't normally be able to carry that heavy weight, but because there's this pulley system, that allows you to do that. We'll talk a little bit more about this a little later on, about why specifically this is happening. Oh, my disappeared. There it is. Okay, so today we're going to be talking about the benefits of machines. There are two types we're going to be talking about: simple machines, and I'll have some examples of that, and compound machines. These are a little more complex machines. And then we're going to talk about mechanical advantage, ideal mechanical advantage, and efficiency of these machines. But before we jump into that, I know we covered chapter 10, section 1 with a sub. So was there anything in chapter 10, section 1 that we want to review?
We'll go over the whole thing. Like,
The whole thing. Well, I'll tell you what, I'll bring that up. There we are. So chapter 10, section 1 was on work and energy. Now, when we talked about work, that's the force applied over a certain distance. Okay? So if I'm pushing on this wall, am I doing any work?
No, you don't know work, it's not moving.
I'm applying force though.
Yeah,
You're
you
doing
don't
work,
it's
but it's not, but it's a waste.
It's through distance.
The waist. Yeah, since I'm not pushing the actual wall, since the wall's not budging, that's the amount of force I have. Let's say it's 100 newtons, and times 0, which is 0. So I'm not doing any work when I push on the wall, but when I push on something else, like this piece of wood here, if I push on that, I'm applying a certain amount of force, probably a small amount of force, and it moved however much that was. So that's doing work. Okay, so it has to be over a certain distance, and obviously some force being applied to it. Jules, talk about that?
Yeah.
Energy. Yeah, good, good. Kind of skip ahead here. We had our work formulas. Work equals force times distance. So fairly straightforward. Now, when you're pulling at something at an angle, instead of pushing it right at it like perpendicularly, then we have the cosine of the angle. Okay, and so basically, when you're pushing or pulling something at an angle, not at 90 degrees, not perpendicular, but at a certain angle, it actually diminishes the amount of, how efficient you are. It's kind of like we talked about pushing on the door at a 90-degree angles is better than pushing on the door at like a 45-degree angle. It's more efficient for you to push at a 90-degree angle. Same thing here. Okay. Typically we use this unless they tell you that there's some sort of angle, and then we use this formula. You guys worked on this problem, right?
Yeah,
Yeah.
it's
Yeah.
very
Yeah.
straight up, so like no angle.
Yeah, no angle because it's straight up. Cool. You guys talked about this?
Yeah.
Carrying 5 books at a time versus 1 at a time?
Same amount of work.
Same amount of work done on the book? Yeah.
Probably faster if you're doing all 5.
Yeah. Now what if the work is the same, right? 5 books at once versus 1 book at a time, right? That's 5 trips. Okay. If the work is the same, what's different? There's another term that's what's different here. Work's the same, but what's different?
Distance.
Efficiency.
Distance,
Velocity.
The joule.
efficiency, joules. I don't hear that word yet.
Velocity.
Times.
Your velocity.
Torque.
Mm,
I know watts is the energy. Or, not
Energy
watts.
for power.
Power is the difference. Yes.
Power.
How quickly,
Power.
right? How quickly you do this work is power. Okay. So if I carry 5 books and I walk over to the bookshelf, right, set down, versus I take 1 book at a time and walk over there, right? Assuming I'm walking the same speed, that's gonna take me 5 times longer to carry 1 book at a time, right? So that means a low amount of power. Right?
Oh,
It's
plus
in a way it's a little easier for me to carry 1 book at a time, right? But we'll come back to this. Let's talk about energy and kinetic energy. Did you guys talk about this?
Yeah.
Okay. This formula here, we're going to talk about this formula again. It's going to come up again. But half the mass times velocity squared. That's a good one to remember. Basically, kinetic. You guys know what kinetic means? Movement. Yeah. So this is energy associated with movement. Okay. So me, as I walk around the room, right? That's kinetic energy because I'm moving. Okay. The energy required for me to do that is kinetic energy. I have a certain mass. I have a certain velocity when I walk. Okay? So you could actually calculate my kinetic energy for me moving across the room. These things we'll review again. We're not meeting next week because we have Veterans Day and graduation. But that Tuesday after that, we'll review some of these again. We'll use some of these formulas. So it won't be the last time you see these. But
When are we taking the test?
we will be taking a test on Tuesday.
When we come back.
Yeah,
Oh,
we're going to review the
okay.
first half of the day. We'll take the test second half of the day. Okay. So, yeah, keep that in mind. Look through these notes. Your test is going to be primarily on section 1, but there will be a little bit on the stuff we're going to cover today. We talked a little bit about power,
Wow.
right? How fast you do something, how fast you do the work. That's power. Okay, the faster you do the work, the more power you have. Okay, slower you do the work, the less power you have, the less horsepower you have, or the less watts you have. Watts, horsepower. Those are different units for power. What do we use in science class?
Watts.
Watts. That's
Watts.
Watts down.
Watts.
You might have heard horsepower.
Divided by 756.
Ah, there you go, 756. Yep. So in this problem, we actually converted between watts and horsepower because you guys probably heard of horsepower, especially with cars and stuff like that. Like the more horsepower the car has, the faster you can do the car that can do that work.
Do they really get it from a horse?
Usually, yeah. I'm not sure. I'm actually not sure where they come up with that term. I'll have to look that up. I'll let you know. My guess would be yeah, but I'll look it up.
No question.
Yeah, what's up?
What's that black thing you just put right there?
Oh.
Recording audio.
It's to hear.
Oh, this.
What's the whole
Looking at the
deal?
screen.
What's the whole deal with like I'm being recorded?
Sorry, all this is to be a teacher, so he's gonna model teaching to other teachers.
Oh, alright.
So we're just recording it, yeah.
It's gonna be like all over you.
I'm Jared.
Not waving at the camera or like.
No, that's bad acting. You don't want to look at the camera or talk to the camera.
Star.
All right.
Yeah, I'll come around with the mic, which is that, and the camera when you guys are working. So just ignore me.
We should put it like secretly in the corner or something, so we wouldn't even like know, and it would have been like more natural.
I think anyway it's going to be noticeable. Anyway, guys, so let's take a look at section 2. So we started talking about machines. We looked at this pulley system, which allowed that girl to lift a very heavy weight. So what, before we don't look at the definition quite yet on the notes, but how would you describe what a machine is? If you had to
It
explain.
does something.
Does
that is
something.
normally harder, makes it easier.
Make something easier?
Yeah.
Okay.
Making the job more efficient.
Making a job more efficient?
And easier.
More precise.
Easier? More precise, perhaps, huh? What?
Do something that you usually cannot do.
Do something you usually can't do? Use a machine versus just your hands or something?
Changing magnitude.
We are the machines. Oh, okay. Actually, in your textbook, the end of the section, they talk about the human body being a combination of machines. So
Like
that is true.
Like a circulatory system.
Yeah. A machine, but defined by physics. I mean, okay. So obviously not a mechanical thing,
Yeah.
but yeah.
We are part Terminator.
Okay, so let's take a look at the textbook definition.
Terminator's good.
Okay, so they say, guys, they say that device makes tasks easier. So, like Shirosh was saying, by changing the magnitude or direction of applied force. So, remember, magnitude is talking about how much, right? The actual number, right? So you can change the force from, say, 10 newtons to 100 newtons, or change the direction of something. So, a pulley system allows me to change the direction, or just a simple pulley allows me to change the direction. So if I want to lift something up, and I'm pulling down, like the girl was, pulling down on a pulley, it changes the direction of the force being applied, right? I'm pulling down, but the force is pushing up. That's changing direction. Now, if I have a pulley system, combination of pulleys, that actually changes the magnitude as well as direction. So if I'm pulling down on a pulley system, right, I might be able to put in, say, 50 newtons, and it might pump out 100 newtons, right, depending on how complicated the pulley system is. So that's one of the things we're going to talk about. Now, that change in the magnitude is called mechanical advantage. So if I put in 50 newtons into some sort of machine like a pulley, and I get out 100 newtons, I just divide the two, and that's my mechanical advantage of the pulley system. So let's take a look at what we're talking about with mechanical advantage. Here we have effort force. So that's F sub E, E for effort. Okay, that's the force I'm putting into it. Okay. The resistance force is the force exerted by the machine. Okay, so this is the resistance of this big weight that's being held up by the pulley. Okay, that would be that. Okay, and mechanical advantage is just dividing the two, the resistance divided by the effort force. So in that pulley example, where I'm putting in 50 newtons and I'm getting out 100 newtons, or I'm carrying a weight that's 100 newtons. Okay, this would be the resistance force, and this would be my effort force. This is what I'm putting in. This is the resistance, the amount of force of that resistance.
So it's like a 2.0 ratio.
So 2.0 or 2, exactly, because we do 100 divided by 50, and that's 2. So mechanical advantage of that pulley I was talking about is 2. Now, there's other things other than just pulleys. There's other machines. So let's take a look at this wheelbarrow. Here we have this person. They're putting in 100 newtons. Okay, that's how much effort, force, that person's putting in. Now he's lifted up the handles 300 millimeters. But he's lifting a 300 Newton force. This is the resistance force. But he's only lifting it 100 millimeters. Okay. Well, let's talk about is the work put in different than the work put out? So we got to think back to the previous section, right? I'll do I for in, O for out. Okay, work in, work out.
Working out.
FD was force and distance.
Yeah, F is force, D is distance. So what can you tell me about the work in? How much work in is this
It's
person?
100 newtons, so that's the force. Distance is 300 millimeters.
Whoa.
So yeah, they're the same.
Tweak that a little bit. Yeah, well, let's change this into meters by dividing.
So 0.3.
My smart board's not so smart today. By 0.3.
So they're both 0.3.
Okay. Yeah, so, I'm sorry, 0.3 times 100 is
30.
30. So that's how much work they're putting in. What about work out? Somebody else. How would we calculate work out?
300 newtons.
300 newtons. Times, and what's the distance they're moving at?
100 millimeters.
100 millimeters. What is that in meters?
1 meter.
0.1. That's right. 0.1.
Yeah.
0.1 meter. Good. So what's 300 times 0.1?
Like 30.
What is it?
No, I didn't. I just
30? You sure?
Oh,
Is it 30?
30.
You guys tell me.
give me a second.
Oh no.
The one and the three.
Now they threw me off.
It's 30. Yeah, it's
30. When you multiply something by 0.1, You just move the decimal in one spot. Okay? Making that 300 into
That's
30. Okay.
All the, I have a question.
Yep.
If it's 100, why are like we're using like 0.1?
Oh, because it's
we're doing
100
this in meters?
millimeters. We gotta change it to meters because that's our SI unit. So, okay, so is the work in different than the work out?
Did this thing.
No, the work is exactly the same. Machines don't change the amount of work that you're doing. Okay? They just change the magnitude of the force or the direction the force is being applied. Okay. So notice, so allow this person to apply less force than what the wheelbarrow and dirt weighs. He has to move it more to compensate. You see that? He has to move this 3 times as much as the dirt to be able to put in 3 times less force than the dirt actually weighs.
Is that why when you move a wheelbarrow, it's a lot more difficult to control? Like when you're
Yeah,
kind
one wheel.
Well, that might be more because it's
The one
balancing
wheel.
on one wheel,
yeah.
and it's heavy. It's kind of top heavy, but you when to lift something up, the handles up, you have to lift them up a fair amount, and the wheelbarrow actually only lifts up a little bit. It doesn't lift up as much as the handles lift up. But because of that, that allows you to put in less force than the actual wheelbarrow and dirt weighs. Okay. You'll see that this is a common theme for all our most of our simple machines. Okay. So the mechanical advantage. To find the mechanical advantage, you would just divide the resistance force divided by the effort force, and we get 3. However you want to write that. Notice he's able to put in 3 times less force than what he's actually lifting, which is kind of a cool thing. That's why we have wheelbarrows.
Why don't you put in like another wheel right there? So,
Another wheel
like right there.
in here.
Yeah.
Well, I mean, you could. It would just be a cart at that point. So you'd lump. He wouldn't be lifting anything. He'd just be pushing it on 2 wheels. Or well, you'd have to get more wheels to balance it off. But yeah. Yeah, maybe a cart would be better for what you're doing. But yeah.
What if the wheelbarrow is really long? Would that make it easier or harder?
That's a good question. So if the wheelbarrow is really long,
You have to lift it up more.
Yeah,
What do you guys
lift it
think?
Higher.
Yeah,
You gotta
so
stick
lift it
it
up
higher.
higher.
lift it up higher.
Lift it up higher.
Because farther out. Okay.
Lift it up higher. What?
So, right. The longer this wheelbarrow is, the more distance, you guys kind of talked about, it has to lift it up higher. The more distance you lift it up. But that also means
Less
the
work.
Exactly. Well, the less force.
Less force, I mean, yeah.
The work's the same, the less force. So the bigger or longer your wheelbarrow means the less force you actually have to use to lift whatever's in there. So if you have long handles on your wheelbarrow, it's going to allow you to lift heavier things with the same amount of force. Cool. Okay, let's talk about ideal mechanical advantage. So, ideal mechanical advantage, sometimes we say IMA, just the first letters, little acronym there, is just the displacement of the effort force divided by displacement of the resistance force. So, this has to do with the actual distance you're moving things. If we look back at the wheelbarrow problem, notice the distance of the effort versus the distance of the resistance is 300 and 100. If we divide those things, we get 3. Wasn't that the same as the mechanical advantage?
Yes.
It was. Mechanical advantage, we divided the force output and effort input But here we divided the distance. These things are related to each other.
How did they how do you think they lifted like the blocks for the pyramids? I mean,
That's a good question. There's a lot of theories about that. People like watch some documentaries and stuff. There's a theory that they used inclined planes, basically to kind of push the materials up. So they have the pyramids, and then they have these big long inclines. Allows them to push these heavy things up. Inclined plane, by the way, is a simple machine. There's theories about putting on rolling logs. That's more to reduce the friction.
where are they gonna get wood from in the desert?
Well, that's a good question, and that's a question they asked about for that theory. So I don't, as far as I know, I don't think anybody knows for sure. There's just some theories about how that might have done.
Yeah, they use the arm.
Yeah, it was
one
the
person's
aliens.
arm
We all know it was
for like a ruler shape, and they use that as like their arm. Like they use one person, and that was like their scale for a ruler for the blocks. 'Cause they're all equal.
Oh yeah, they did have a measurement system there to make sure all the blocks were the same length and everything. Yeah.
So they use water to water up the soil and then push it.
Where are they gonna get, again, water from in the desert?
Well, they have the Nile.
That's a lot of like water.
water in the desert, dude.
But so I don't know, but there are some good documentaries that have some theories about it.
Ancient aliens.
Either way, it's a lot of work. There might be some documentaries about that too. But I mean, if you want to watch Stargate or something, you can get into that. But I don't think it was aliens. Okay, so let's talk about efficiency of machines. Okay, so right here it says the ideal machines, the efficiency is 100%, which means you don't lose any work that you put in. Okay, if I put in a certain amount of work, I get the same exact work out. In the examples we talked about, like the wheelbarrow, that was true. Got the same amount of work in and it's out. But ideal machine, or I'm sorry, that's an ideal machine. Okay. In the real world, that's not how it works. Okay. In the real world, machines have efficiencies that are less than 100%. Okay, the work you put in, you don't get all of that work out. Okay. Why do you think that might be the case?
Friction.
Yeah.
Friction, air resistance, gravity.
Yeah.
Hold on.
Air resistance and friction are the big culprits there. Obviously, air resistance is a type of friction, but there's frictions within the machines, and there's, if you're here on Earth, right, there's air resistance outside of the machine as well. So those things will limit your efficiency. Now, to reduce friction, that's why we have things like machine oil. Right? You have machines, you get some oil in there, WD-40 or something like that, and that makes it a lot less friction. There's still friction there, but it reduces friction significantly, which increases your efficiency.
Oh, that's static friction.
Static friction, yeah, things like static friction or kinetic friction, those all are in the machines, all in play there. Okay. Let's take a look at this. Go ahead and get your physics textbooks. Take a look at these two problems, mechanical advantage and ideal mechanical advantage. You're welcome to work with each other on this.
That's not camping.
Yeah, you're on camera.
Page 277. Notice on page 277, there's several different types of simple machines in the diagram there, and there's formulas that go along with it, with each type, to find your ideal mechanical advantage. go ahead and take a look at the problem. Through it. You reading it, George?
Yeah.
Okay.
Doing this
I'm
one.
gonna ask you what the answer is in a little bit.
Well, I don't know the answer.
All right.
I read it. I can read it for you.
So you went and read it?
Well, start with reading it.
I can read it for you.
To get the formula.
Yeah. What's the answer,
We're
Chris?
talking, well, the wheel and axle also.
Is that one already used?
Camera, we go.
Yeah, well, actually, okay, so guys, for these, the ideal mechanical advantage, it's also right here in the notes. So you can use this as the ideal mechanical advantage. So what do you think? How do you find, let's start with ideal mechanical advantage. How do you find it?
Go back.
So when before you divide it.
You gotta put the D as your D on. That's
But I knew there was either two outs or two Chris's, and I guess it's two Chris's.
displacement of
Is he the one right here?
right here, right?
So where are your two displays?
Oh.
It's gonna be 40 divided by 10 to the ideal mechanical. Is it when it's the displacement of the displacement of the
And tan is the effort force.
Okay,
Well, look at the force exerted. This is the effort. This is that's the effort. Yep. There you go. Do you guys see what to do here?
I know this is the force exerted
Right.
on the user, right?
Yeah.
Okay. And then how do we find like the resistance force?
That's a good question. Talk about that, but if you're not sure, go on to IMA.
Okay.
So this looks like a triangle.
Yeah, it is. To get the
Because it says a force.
Yeah. Well, no. In this problem, no. This
That's
just
the distance.
Genius.
this just is more
You guys are
mathematics.
so smart.
So
Which way you're pulling it.
Well, I should know.
Pull it straight down.
So for the MA,
It's
don't-
F over F5.
No, we'll just use the formula.
show up there like the test.
so make them this here.
Wait, what's that?
Yeah.
Yeah, I'm gonna do like this, right? Like,
It's the displacement.
Yeah.
If you're applying 1.4 newton.
Oh, you found the loop.
Right.
Yeah.
That what you did?
Yeah.
Ah,
We
okay.
just have to make
Well, that's
So
good,
DE
but
is
it's,
what?
you don't have to find the work to find IMA.
40.
Okay, well, I put
How's
these
that
both
for?
in work.
It's
It's
the distance,
So 40 divided by
Oh, it's done.
I put both works together.
Yeah, we got.
and then is DE 50 or DR?
No, it's 10.
40.
Usually 10.
Oh,
10 centimeters.
Hey, you gotta ask for help.
All of it?
Yeah, I asked for help.
Yeah, I know. I get to still.
So you're working on this?
I did.
Yeah,
So is IMA?
Yeah,
We'll label that.
That's what I got for IMA.
So couldn't you?
He's like, I don't know.
first telegrams to get it in shipping? I know you have to pay for one reason to get it.
IMA, good.
So O bar and F.
Think about MA. Can you find MA?
Resistance.
Please bring that around.
Oh, sure.
Good question for this. We got converted one of these to kilogram, right?
So
To be able, but don't we Don't we use that to find the MA?
For the force,
Yeah.
yeah. So,
I gotta get a
So we have one that's one in newtons and one that's in kilograms. So we need to convert it so that our things are the same.
yeah. So you can convert kilograms to newtons, right? How do you do that?
Divided by 1,000.
No, I don't think so.
when they're called girls grenades.
Is grams and newtons?
He said
No.
like,
I don't know.
yeah, I believe.
I'm lost.
Newtons is weight, right?
Yes.
Yeah.
You guys know how to find weight or
Oh
something?
yeah. I don't know.
What do you do?
For the SI
No.
unit on
You
this?
do it like in every chapter.
Yeah.
For the SI unit, what
It's
do we
not
do?
in this segment.
Don't.
For that looks good for
But doesn't it have an SI unit?
huh?
Doesn't it have an SI unit?
SI unit. No, for IMA it's just a ratio. It's just a number. No
For
units.
MA?
MA?
Same thing?
Yeah, same thing. No units for that.
But it looks right?
Looks good. Yeah. I'm not.
It's a little fixie.
I don't know if you found.
Like right around
I don't know how you found
the
MA. Where'd you get the point 4 and point 1?
Why? I turned it into meters.
Don't we find force and distance to find?
Yeah. So for MA you gotta divide the forces, right?
Yeah.
You have one force, but you don't have the other force, right?
Yeah.
Wait, what?
You have one force, the effort force,
Mhm.
but you don't have the resistance force, right?
But to find the other force, when we just times it by
Like this.
I know we have done it.
Because then wouldn't that make it any
Why
more?
10?
Bill 9.
Can't really find
Because it's gonna be
Bill?
just-
No.
We gotta ask Bill.
Okay, just-
There you. Oh, that's to find work, but you would have to have that in meters anyway. But no, we're not finding work. We're finding weight.
Yeah. Trying
No, they're
Yeah,
not
find the
really
weight of this thing.
Time to look at our old.
Yep, look in your old notes.
No, isn't intense gravity?
There you go.
9.7. Yeah, I was
That's
like,
it.
I was like, we have done it so many times.
I know. I was surprised I forgot.
Yeah.
So it's 0.50 times
What?
9.78.
What? So no stupid jokes?
Is what between?
It's
It's the 0.50
It's like, I'm not
times-
Maybe. I'm trying to like narrow down the answer.
legit though about the snail.
Yeah.
And like,
Can
I
I
didn't
make
really know,
calculator?
dude. Like people were bagging and stuff. I
Roche,
seriously
are you working on?
I got IMA, I have no idea how to get
You got IMA like 3 minutes ago.
I'm in
Yeah.
MMA.
IMA is just blowing my mind, so I have no idea.
So
Do you have any of those forces?
I have 50 kilograms.
9.78.
Is that a force?
Yes.
Oh, you have the 1.4.
That's a weight. Max.
Mass.
So,
If it was a weight, that would be force. But
Big
how do you find the weight of that?
Chris has got it.
IMA is
So I helped you with IMA, now you help me with MA.
Wait, so we multiply it?
Maybe.
Wait,
Let's talk about that.
multiply this
when I
to
did
the
this-
force.
Alright guys, let's talk about IMA first. Let's talk about IMA. So for the ideal mechanical advantage, how do we come up with that?
4.
40 over
Four?
10.
Yeah, I got 4.
40 over 10?
Yes. Which is 4.
Okay. Now, he changed it to meters, but he got the same thing. So he did 0.4 over 0.1. But either way, what are we getting?
4.
So whether you have it in centimeters or meters, because we're dividing these, we just still get the same number. Okay, so we have ideal mechanical advantage. For MA, this, here we have a force. Is that effort force or resistance force?
Effort.
Okay, so let's jot that down. Is it effort?
Yeah.
Okay.
It is.
Alright, how about resistance force?
You gotta find it.
No, I thought resistance force.
Oh,
is
it's
the-
4.89?
is The 1.4 is that force. isn't it?
It's 5.
It's 4.89.
I got 4.89.
It's
4.89?
Well, if you round it, you
Yeah,
get
it's
5.
times-
Okay, how'd you get 4.89?
You multiply it by the gravity?
Ah, okay. So we took the mass of the resistance, we multiply it by gravity, and that gives us the weight, right? That's how much force we're lifting here. So well, again, we'll do 0.5. That's the mass times gravity. And
4.89, so 5.
4.89.
8, 9.
Yeah, but no, if you round that, that's just 9.
We only have 2 sig figs, so let's say 4.9.
No,
Nine.
yeah,
Yeah.
4.9.
Makes
that's
sense?
what I meant. What about 9.78? Not better.
9.78. Yeah, you can use 9.78 for gravity. Sure. Okay, so we have the effort force and we have the resistance force. How do we find mechanical advantage?
You do the 1.4 divided by.
1.4 over.
Like, you do the thing and you do.
Oh, wait. Let me hear Nick.
1.4 divided by 4.89.
1.4 divided by
4.9.
4.9. Is that right?
Yeah.
Okay. So
I thought it was all the way around.
mechanical advantage is the effort force divided by the resistance force?
No, it's resistance force divided by effort force.
Oh, okay.
No, wait, no.
There we go. Matt's got it.
Wait, I also thought.
So can we fix this?
Yeah.
We can.
Do you want your first one?
Nick, can you help us fix it? Guys, quiet down.
Like, it's FR over FE.
Yep.
Like,
F
I like
of
where
R.
it is.
Nick is extra smart today.
I took some, like, smart pills.
There we go. Ate some smart.
So, 1.4 is FR.
And drink some more
No,
water.
I think
FE,
what-
FE, yeah.
FE?
That's what I meant.
So what goes over what?
It 4.89. I mean 4.9 over 1.4.
All right.
Damn, my brain's on overload.
Good stuff. That's correct. All right. So when we divided this out,
3.5.
we got
3.5.
3.5.
Yes.
Ah. Okay. Cool. Now, somebody asked, is the mechanical advantage the same as the ideal mechanical advantage? Well,
No.
is it?
No.
No.
Very.
0.5 difference.
Why isn't it?
Gravity, friction, and air resistance.
Not really gravity. Gravity doesn't really
Gravity
play
doesn't-
a part. Yeah, but friction. Yeah, the different types of friction is why this isn't working. So with a pulley, right, or a pulley system, you have rope that's being dragged around like a spinning wheel on a pulley, right? There's friction involved, right? There's a little bit of air friction as well, lifting the weight or moving the rope through the air. But I think probably most of the loss in work here, it has to do with the friction of the rope rubbing against the pulleys and stuff like
On a perfect planet, it would.
that. In a perfect world, an ideal world, right, it would be 4, right? This is what our perfect pulley system for this example would be. But this is what we're really getting, 3.5. So what's the efficiency of our pulley?
3.5.
Let's look at the efficiency formula. Let's write that out.
Less than 100%.
It is gotta be less than 100%. That's right. Where's that efficiency formula?
Oh, WO divided by WE times 100.
I would think that would be.
George, do you have your efficiency formula? Oh, Rob.
It's complete.
I got
What-
84.25, but that's
Which
because
one
I looked at
out?
3.4 now.
I think that's
What?
3.5.
Work out into what?
You do it.
You get it?
3.4. Oh, you used 3.4 now.
Yeah.
Okay, so
That's
then
road.
round it.
You get the work
No,
out.
Yeah, that's good.
Did you use workout
By
workout?
100?
How many calories do you have?
0.8.
Oh, wow.
It can't be more than 100%, though, right?
No, not
Like you said.
It's
0.5.
ideal machine is 100,
You see how that works?
but in the real world, it's gonna be less than 100.
That's like
So, did you write out your efficiency formula?
I'm looking at
You
it.
understand?
Jot it down. Jot it down next to the
You
problem.
have to eat like
So
It's like-
your
you have
app
to eat about a
here
dozen.
for this one,
You don't burn it down.
and then you plug it into your formula and you times by 100.
You get 87.5.
Yeah,
Now,
you
what's the
see?
percent? Like,
Okay.
Illy.
What?
You get
Illy.
87.5.
Yes.
Billy? She's Bill.
So then
Yeah, that's
you
you.
see how you work out and you work in.
Do we still have to worry about stupid?
So then you
Rush,
divide
work on your problem.
I did. I got 8.75.
That 8.75%.
Yes.
Okay, like write it down.
Okay.
Do we still have to worry
So
about
you have your
stupid?
E and then you have
So
your
there's only
equals.
like-
And so your work out
Yeah,
is
we'll always worry about
3.5
sig figs.
divided by
So
and
what
your
does
work
this mean,
in
90%?
is the 4. So then
we'll
you enter in
do
your
sig
calculator,
figs.
you divide
Well, I
the
mean, there's only
3.5
one. We got
divided by 4, and then you times that.
Is that
and
work in,
divide
work out?
100, and that's how you get the
Or is it mechanical
47.
advantage and ideal mechanical advantage?
Yeah?
Oh, that's true.
Gotcha,
Yeah.
I got you.
Guys, make sure we're using work in and work out. And you guys, a lot of you guys are using mechanical advantage and ideal mechanical advantage. So how do you find, let's do work in together. How do you find work in general? What's the formula for that?
Force and distance.
Force times distance.
No, we did it right.
Hey, guys.
We believe it was right.
Alden is an amazing teacher.
Switch. Alright, so what's the force in?
I got.
Rosh, what's the force in?
Force in.
Yeah.
1.4 newtons.
Good.
Wait, yeah.
What about the distance? What's the distance in? Or exerted?
40.
40, ooh, is that in
centimeters,
SI?
and it's not in meters.
So how do we get into meters?
4 meters.
Divided by 100. I mean, divided by 100.
Divided by 100.
4 meters.
0.4.
0.4 meters.
Okay, cool. Let me move this guy over. Okay, so we got work in, and what does that give us? Work that out. 0.56. Suresh, is that what you got?
No.
Let's work that out. Double check that answer.
There's like no space left, so I'm just gonna.
You got backs of. There you go. Alright. Once you have this, take a look at work out. We have the force. We have the distance for out. We can calculate that.
Okay.
I'm getting like a different answer.
The funny thing is, I did this on accident like a lot earlier.
What?
Work.
What we're doing right now.
True.
What numbers did you use?
So what's work out?
Working out to like 0.56.
Did you use
Point.
this force?
No, I'm just kidding. It's like
Going to.
And
No, I used the.
All the-
That's what I got for the workout.
cool. Okay.
Now if you ask me that. Would you go?
Yeah. That's
Did you get this?
I just
I
remember.
got, okay, I got 0.35 for the all force.
Okay, good, good. What goes over what? What's divided by what?
Oh, you didn't get it.
0.56 divided by 0.35?
Is it?
Come on, man.
No, never.
Does that give you more than 100%?
No, they gave me weight less.
Well, I'll give you 1 point something, which is
Yeah.
over 100%. We
Oh.
multiply by 100.
Oh, okay.
That's the news, right?
Wait, is it 489 or 0.6?
That's the same as the resistance force.
Oh, okay, never
And
mind. I got it.
then it's in centimeters,
get it?
right, the
Yeah.
distance?
62.
Yeah, so it's 0.5.
Okay.
And when you multiply that by 0.1, you get 0.489.
I'm glad
Is that what you
figured out
use?
this problem.
Wait.
Yes.
I'm not talking.
Next time I got 30 money, I really want to get the burrito.
And then the
It's like,
But it's changed at the meters.
oh, so
Wait.
divide by 100?
Divide by 100 to get the meters.
7% efficiency.
Good.
But I didn't have to do all that work. I just did it.
Yeah, no, it's good. You're supposed to get the same answer. I'm going to talk about it. It's talking point.
But
Wait, so you
why'd you
missed
make me
all
go
my
back?
work and redid it?
He made me go back and I did the same.
I just like to mess with you, Mark. Alright, so let's talk about work out. what was the force out?
4.89.
I work out.
You got caught on Snapchat, dude.
Yeah, it doesn't feel so good now, does it?
All right. So force out. What is that?
4.89.
4.89. 4.89, which is the same as the resistance force. Okay, that's the same as force out. When I say force out, I mean resistance force. Okay. So you want to use that number. Some of you use like 3.5. That's not a force. What about distance?
So if we use 4.9.
0.1. Good. Does everybody see where we got 0.1?
Yes.
Yeah.
Times.
It is?
So we multiply this out. What do we get?
Well, it's 4.9, I got 0.49.
0.49?
1.48 now.
So if we round to sig fig, sure. Okay.
0.489.
Such a fancy word.
Yeah, if you use 0.9 and 0.489, either one is just fine. Okay, now we can plug this stuff in. Okay. What's our work out?
4.429.
0.49 or 0.489, whichever one you want to use. And divided by what? 0.56.
Yes.
Good job.
And when we divide this out, what do we get?
0.875. 0.875.
Okay. And when we change that to a percent,
Yeah,
Multiply
move
by
the sig figure.
multiply by 100 to change to a percent.
That's a high efficiency.
So why
It's not bad.
did we get the same answer when we did it the other way?
Okay, good question. So,
Wait, I want to know why.
she asked, why did we get the same number here as we did when we just divided the IMA and the mechanical advantage? Okay. If you look in your textbook, there are two formulas for efficiency. The first one that I showed you is with work. The other one is a nice little shortcut for when you do problems like this. That's on page 276. Okay. So take a look at page 276, Roche. Take a look at that.
Efficiency equals
Staring through this? Yeah, it's done.
Oh my god,
Take a look.
How would you guys though?
Yes.
Good.
I'm not you. I'm the eraser.
Yeah, you got it.
Okay, guys. So my point is, eyes up here. My point is, either one of these formulas will get you the same answer. Okay. I wanted you to use the formula that we used with work because, well, maybe on the test that will be more applicable. But you do know that there's another formula that we can use that might be a little bit easier if we've already found mechanical advantage. Okay. So either one of those formulas works. Don't worry, guys. We will review this a bit. Next time we meet up, we will review this a bit. So this won't be like the first and last time you see this. Okay, now for simple machines. What kind of simple machines are there?
Hammer.
Screws. So let's talk about in general, and then we'll talk about the specific ones like axes and hammers and stuff like that. So there's inclined planes.
Wedge.
Example of that is here. There's a wedge. There's your axe.
Lever.
Lever. We've talked a bit about levers, haven't we?
Yeah.
Lever arms.
Yeah.
There's different types of levers. Hammer is an example.
Seesaws.
Wheel and axle. Okay. Your handle, door handle, is an example of wheel and axle. Also, you have those on cars. Yeah.
How are those inclined planes?
This guy right here.
No, wheel, axle, and.
They're separate.
Oh, this is separate. Yeah.
All
These
right,
go
right.
together,
Separate colors.
and then these go
I thought we were
together.
just going straight across.
No. Okay. A screw is a type of simple machine, and a pulley. That one we've already talked about a little bit.
Buckets.
So I have some simple machines up here. I have a hammer. what kind of simple machine is a hammer again?
A lever.
A lever. Yeah, a lever. Now, this part of it, when you wedge it underneath the nail, that's that would actually, I'd argue that's an inclined plane. But you could say if you're like hacking into something, that could be used as a wedge. Yeah. But for the most part, this is a lever. When I hammer something in, okay, that's a lever. Okay. The lever arm is the length of the hammer. The longer the hammer, the more mechanical advantage this hammer is going to have. If I choke up on the hammer and I hammer like that, it didn't really go in very much, right? I just lost a lot of mechanical advantage when I choked up on the hammer. The longer the lever, the more mechanical advantage I get. The other part of the lever is when you use the other side of it. So we use the inclined plane to kind of get that underneath the nail, and then when I pry this, right, that's a lever as well. Let's see. Does somebody want to pull up? Can I get a volunteer to do this? Yeah. Come on up here. Okay. Can I get another volunteer? Come on up. Not yet. Not yet. Come on up. Okay.
Taking people from the audience. Can I get a volunteer?
All right. So he's going to use a machine, and you're going to try and pull it in. If you want to use this, so you no, you gotta use this, and we'll see who has an easier time with it. Go ahead and try it out.
Wow, so much work.
Okay. You're not done yet?
Struggling.
That's okay. I don't expect you to pull the nail off.
That wasn't even good one.
Okay.
I mean, I put
So
that like a centimeter out.
that's pretty good. That's pretty good. All right. So. All right. So why was it easier for Matthew to pull the nail out?
He distributed the weight and the force.
He got a lever arm.
The force. He distributed.
It has to do with the lever arm.
Oh,
Okay.
so that's
That lever arm gave him more force to pry it out than my fingers just trying to pull it out.
Okay. Yeah. So the lever arm gave him more force out than he was able to do with just his fingers, right? He didn't have like a big long lever to pry this out, and that's why it was tougher for him.
What are we gonna do now?
Now we're going to talk about another one.
Well,
Do you want do you want to screw this in? You're my volunteer. There's a little hole there for the nail.
Good job, Martin.
we need a volunteer here.
Okay, so as he screws this in, there's multiple machines in place here. One is
Splitting the wood.
this thing right here, the screwdriver. What kind of machine is this?
A wedge? Maybe.
A wedge, maybe? What kind of machine is this?
It's a stick with an edge.
Okay, if we call them these,
It's a screw.
what category are these
Oh, I
six
forgot.
machines here?
It's a
Is it
wedge.
a
it's a
lever?
wedge.
A wedge. Now,
Wedge it in there.
it's a
part
wedge
part
if
screw.
you kind of
Part
pry it
wedge,
in
part
there
screw.
and
Screw.
Part wedge,
It's
part
screw.
screw.
But he's turning this. So what is this?
Part wedge, part screw.
A what? A screw. Well, the screw is actually another machine. So the screw is one machine, but the screwdriver is a different machine.
Wheel and axle.
Like a wheel and axle.
Ah,
Axle.
yes.
Wheel and axle.
The screwdriver is a wheel and axle. The screwdriver is a wheel and axle. It's easier, maybe not that easy, but easier for him to screw this in because it's a wheel and axle. Now, if I tried to turn it just with my hands, of course, without any machine, without any tool, I'm just not able to do that. Yeah, with your nails, you don't want to do that. Your nail will come right off.
Yeah.
But with a screwdriver, you are. Now, let me kind of explain how this works. Like the wheel and axle, this is a rotating thing. This is your axle. This handle is your wheel. the wider the wheel is, the more mechanical advantage you get. The bigger, wider that handle is, the better mechanical advantage you have.
So I should put bigger wheels on my car?
We'll talk a little bit about bicycles, and we can relate that to cars.
Thank you, Mark.
But
We love you.
okay, so there's a couple things.
Encore.
There's a couple things that are going on. There's the wheel and axle, which is a screwdriver, but there's also the screw. Now, if you look at the screw, it's a little different than a nail because it has these spiraling grooves through the nail, through the screw. Okay, that's the difference. So, it's obviously I can't push this into a piece of wood, right? I need a screwdriver or something, right, to kind of push this and drive this in. But notice how much distance my hand is actually moving and how little this screw is actually moving, right? As I do a full turn, right, I just rotate the circumference of this wheelbase and I only move the screw in just a few millimeters. Right? All of that difference in distance gives me more ideal mechanical advantage. Right? Ideally, this is actually a pretty powerful tool, right, for driving the screw in. So keep that in mind. Also, on a screw, there's different types of screws. Some screws have these grooves are spaced out more, and some these grooves there's a little less spacing between. The less spacing there is, the more you have to turn it to go in farther. Okay. The more spacing there is, the less you have to turn it to go in the same distance. It's harder to screw this in when the grooves are spaced out more than it is if the grooves were spaced out much smaller. It would be easier. You would use less force when the grooves are smaller. So it gives you an idea of why there might be different types of screws and how some screws are actually easier to screw into something than others. If you're screwing something into very hard material, you might use something with narrower grooves, or you might just get a bigger screwdriver with a wider handle. Well, you're a power tool, yeah. Power tool would be the best. Now, there's other tools, and they're all over.
So excited to get it.
They're all over the room here. Here's a simple machine.
Stapler.
There's a complex machine.
Don't put that to your
Yeah. This guy here, I push down on this here, and it staples, right? You all know how it works. What kind of machine is the stapler?
It's a wedge.
Inclined plane.
Wedge.
With a wedge.
Screw. In a sense.
There is an inclined plane in a stapler.
A lever.
And a lever, yes. The arm of the thing is a lever. The fulcrum, the rotating point, is right here. And the farther out this stapler, the more power, the more force out that I can get. That's why where I have a stapler for more papers with bigger staplers, right? Notice this arm is farther out. That gives me more mechanical advantage. It allows me to staple through more pieces of paper. That's why these are designed a little differently.
And it has a red thingy.
Now, the inclined plane is right here where the staple runs into. And that's the inclined plane folds the metal staple in around the paper. So that's where the inclined plane is. But we don't tend to think about that. So stapler has a couple simple machines in there. What about scissors?
Wedge.
Wedge. Good.
Wait, not wedge.
What part is the wedge?
Blades.
The blades, yeah. Kind of like how an axe would work. The scissors work the same way. But there's another simple machine here as well.
Lever.
Levers, yes.
Right there.
The handles
The thing.
are the lever. The bigger the handles, the more mechanical advantage you get out of your scissors, right? So when you have heavy-duty scissors, you sometimes have longer handles. If you have those little kitty scissors, you can only cut you can only cut through so many papers. You know, they're only so powerful. The little kitty scissors don't give you much mechanical advantage.
But they,
Talking
I
about
hated those in elementary
Well,
school.
you don't
They
cut
just
yourself.
gave you the little scissors, and you needed the big ones, you know.
I know.
Job done.
No,
They
you
don't want you to
sit
cut
down
yourself.
paper, pull it down.
That's
go
what I
real hard.
did.
No, I mean like for little like art
No, I know.
pieces.
You just read those.
Yeah.
How?
It's not that easy.
You
Take the paper.
Okay. All right. So oh, this is just a little joke I found. Scroll down. All right. You've won your bet. You can lift me with one hand.
Oh, okay.
So
Monkeys can't do that.
Good job, Nick. Good job.
okay. So because there's a complex pulley system. By the way, the more complex, the more pulleys it has. Actually, the more mechanical advantage you tend to get. Because of all these pulley systems, the force in is probably fairly small because they can only put so much force in. And the resistance force, of course, is quite a bit. Right? So these machines, and especially the more complicated ones, can allow you to get a lot of mechanical advantage here.
Could it get to that point, like, say if it was not a monkey but like a person, like they can lift and with like a complex pulley system?
Yeah. I mean, I can lift a car. I can lift a car with my foot.
Yeah.
Yeah. Well, with a jack.
Jack, yeah.
With a jack, right? You push a little bit, and you have to push a lot, right? You have to move your foot a lot for the car to go up just a little bit. But yeah, with my foot, I can lift a car. So this isn't out of the question. We'll actually talk about jack systems a little later when we talk about force and pressure.
Jack.
That's a couple chapters from now.
I wonder why it's called a jack though.
The Jack made it.
Yeah, that's what I was thinking.
All right, so compound machines. We actually have some examples. So we have some examples of compound machines. This was one. We said this was a lever and an inclined plane, and the scissors were another compound machine because you said it had a wedge and a lever. So basically, a compound machine is just a machine consisting of two or more of those simple machines. There's a lot of compound machines in the world. There's a lot of them. So scissors was an example. The stapler was an example. And then, has anybody played Mousetrap?
Yeah.
Well, we haven't. That's what the game is. Basically, like you push something. I can't remember where it starts. This mayhem.
I think it's up there by the thing here.
I think you push something over here. The ball goes down the inclined plane. It goes down this inclined plane, hits something else. But there's a lot of little machines, wheel bases, levers, things like that, all throughout. This is kind of the epitome of a compound machine.
Isn't that a Rube Goldberg?
Isn't that a
Rube Goldberg? Is that what it's called?
Yeah. We have all these different simple machines all connected, and they do something fairly simple, like trap a mouse.
Yeah. Reminds me like those things where people like
Yeah,
make
let's
these
look up a
things
Rube
so
Goldberg.
complex, and it's like, nah, I don't want to set that up again.
It's like 51 or something.
All right, so here's some more compound machines. I got this online. It is a little bit dated, but I thought that was, I actually kind of enjoyed how dated it was. Anyway, it says some early uses of compound machines. Things like a stone axe. An axe has a lever, right? The longer the axe, the more force you're allowed to do. It also has a wedge, right? The actual head of the axe. This, kind of like scissors, right? Has your wedges, has your levers.
Cut those leaves.
Wheelbarrow. We talked about the longer the wheelbarrow, the more mechanical advantage you get, right? That's because these are levers. And then over here you have a wheel and an axle.
It's not a very effective wheel though.
These are your early compound machines. I kind of enjoy this one because it says today's compound machines, but of course
Typewriter.
this is This is probably from a few decades ago. But yeah, all of these, pencil sharpener, bulldozer. The lawnmower and bulldozer haven't really changed much, but obviously the hand drill is a little dated. Typewriter, we don't have those anymore.
Hand drill, same thing as a pencil sharpener.
Yeah, no, we have fancy sharpeners, yeah.
Actually, the pencil sharpener, same thing as a hand drill.
One of those hand drills?
Oh yeah, very similar. Yep.
We have electric ones now.
And it's I
They're both electric.
I do. Okay, so you guys get the idea. So there's a lot of compound machines out there. These are just some of them. We're actually going to kind of brainstorm. What machines do we see on a day-to-day basis? I've shown you a lot of these. So we're going to get into table groups.
Maker alone.
I know.
Well, they can work with us.
Yeah, you can work all together.
Let's go with them.
But I don't want to like be all speed up on there. Yeah, this guy knows.
Okay, so you have
So now
groups.
I have to go over there?
Yeah, come on over.
No, you just stay
Okay, I'm staying with them.
Okay, so we got a group here. You guys group. You guys group.
For this, can we just do like the same machine if it's for the garage, like the garage door thing, and then you have
Yeah,
then
if you
the
can't
door
think of
itself?
another one, yes.
I mean,
Try to think of different ones, but if you only do one that applies to a few, that's not okay. So you all have a handout here, right?
Yup.
Yes,
Take a look at this first page. These are various rooms in your house, or typical. Think of it about your typical garage, typical bedroom, typical kitchen, typical bathroom.
What is the?
You can think. Well, yeah, that's a good question. But you think about what might be in your bedroom, or just what might you've seen in any bedroom. Okay? And think about what kind of machines. They can be compound or simple. That fall into these categories. So when we look at a garage and gears, what kind of thing might be in a garage that has gears?
Garage door.
A garage door or garage door opener?
Yup.
Okay. You can write that down if you want. Try to come up with as many different examples of machines. Try not to use the same one. Okay? Try not to use the same machine. And go ahead and jot them in.
Well, we need an ink page for-
Alright guys, I'm going to give you some time to do this. If you have questions, I'll walk around and help you out.
everything.
But
Guys, put everything in the same rule and axle so they just put the door in anywhere.
I know, because I don't have
Doors.
No, try to think of something different. There's other things that are real next.
I know they're.
Well, then write them down.
Just write it down.
Not door every time.
Alright, I'm gonna do the 2 and 2.
What does it mean by gears?
Gears.
Yeah, man.
Well,
What is a gear?
that has gears in it.
Oh, so like if
Oh,
the bedroom,
I
so like
guess the
your
gears
door
don't
handle.
put any left to it.
Yeah, the locking mechanism might have gears in it.
for garage, the wheel and axle, the door from your house to enter to the garage.
Oh, yeah.
Why don't you sit over
Garage.
here with Miguel?
Like the door to like enter and exit.
Yeah, enter, exit from your house.
got one?
to the
That's
garage.
true.
He's bringing up like 4.
Is that used
You can help each other out.
What's a wedge?
Think about what might be there.
What about the bedroom?
Does it have to be?
That was a lever on
The
it.
doorknob.
Does it have to be legal?
Your door. This is
Hopefully.
I'm afraid to ask.
your kitchen has a
Wedge.
So it could be like anything in the garage.
and a bathroom.
Yeah, anything you might see in your garage.
Well, you would see
Shower
screws
door.
in a garage, like connecting like like the wood and stuff.
Oh,
whatnot.
connecting the actual garage together.
Oh, think about all the different types of levers.
Yeah, it's like
Go down
doors,
the hall.
yeah, some.
Cool.
Nails
Is
connecting.
my curtains like a pulley, like in the restroom?
Not really.
Connecting walls.
What is it?
Yes.
Does that say orange?
I don't know.
I was
What about a wedge?
You can go back to it.
Like,
Just throw that in there.
Well, like you can use a
Door
wedge.
too.
You can use a wedge to like open up your door. So you know, like your door, they have door stops.
for wheel and
And that
axle,
counts as
and
wedge,
the door
right?
knob.
A door stop
Doorstop as a what?
as a wedge.
Oh, yeah.
But in the garage,
Yeah, to open up a garage door, like the back door or something, you know, get out of your garage. I use them.
Anything you can do in the
I don't know, I use them.
As long as somebody somewhere.
But yeah.
Yeah.
So what was for wedging? I'm sorry.
A door stopper.
A door stopper.
like low B.
Yeah.
Because the mic have to be right here.
Good amount.
Have to be extra smart.
Door stop.
Okay, a pulley.
oh, you just know.
We need a pulley system.
Hey, quick question, Kat. I don't have a garage, but let's say if you can't, like the door doesn't open.
You would-
Isn't there something to
Yes.
like pull it?
No, you would the doors when that happens, your doors normally open. So like if your door's like this, it'll open up like this. So like you'd like lift it, like so you'd have a
Yeah.
handle right here and you'd lift it up.
Yeah.
But it wouldn't like I don't think it'd be a pulley.
Pulley.
Would it be a pulley
Even if
system?
they go like this,
Hey,
you just
what?
like
Hey,
push
what?
it up.
No, it wouldn't be a lever that thing. No.
Oh yeah, yeah.
I think it'd be an
Or like,
inclined
a
plane.
board.
No,
You know, like a
because
plane,
we're
lift it up.
what
It's
we're
not like-
talking about is the handle, not like
For
how.
an incline plane, what about the stairs?
I don't have stairs in my garage.
So pushing it.
Ramps
I
in
know
the
mine
garage.
doesn't either, but some do, especially if you come from your house to a door.
Well, you might have
You know, some
ramps.
houses will sit up.
I never
Oh,
seen
an
that.
incline plane. You know, like for like the disabled. You know how you know like for like disabled, like to get into entrances, they have like instead of steps, they have the.
Ramp.
I'm gonna start. I let you girls with the garage. We're gonna start the bedroom.
Okay. So an incline plane can be like, yeah,
A wheelchair ramp.
for an incline plane. But that could be for like any entrance.
Yeah.
I don't know. We'll put it right there.
Lever.
A lever.
Hey Chris, what do you have for bedroom?
With a lever, that's a wedge because the little spikes wedge between your hair.
Well, that could be a wedge, yeah. But it also has a lever on it. Comb.
Yeah, this is like a
Oh,
hard
lever.
skin.
What has a wheel and axle?
What is that? Door handle.
Alright, what about like when you're in the kitchen? Alright, you know when you're in the kitchen, you have a pot and you put that.
Alright.
The thing that covers the pot on top.
Lid.
A fan works as a wheel and axle, right?
What does that work as? That could be like a pulley, right? I don't. A lid. Pull it up.
How many do you have?
A couple. Wow.
Let me get some, yeah?
Yeah.
Yeah, pass yours over.
Pass them
Is it give and take?
We got chopping.
No, it isn't. I thought that's what
Hey, just quick question. Do you guys have an
I
incline
have a shower knob for wheel and axle.
No.
A shower?
A shower knob.
You know how to
The
turn
water
it to
pump.
turn on your
Shower knob.
water?
What is that? The faucet handles? There you go. Oh, the shower knob.
Like a like the.
That might be a. Okay, you guys ready? What are
So I'm not sure.
Alright, kitchen.
Yeah.
Stove.
Oh, it has like a little.
Oh,
Yeah, okay, sure.
Yeah. Stove for a wheel and axle?
How does that?
You know, to turn on your
Okay.
flame.
What about gears?
Stove knob.
Knob.
Gears in the kitchen.
Lights.
I don't know what has a gear in it.
Although in the kitchen, there's a lot of it.
A blender. Your blender.
Yeah.
Coffee maker.
Blender. Like, we said an axe was a wedge, right? They start off an axe. And then what else do you have that's like a knife? That's a
Actually, that's a great question.
I have an axe.
Straightening knife.
What in the world has gears in the bathroom?
What can be a
One of those like
Like the possibility of what could have
You know
used
when you're
screw.
blind and you pull the string down?
That was good. Wait, what? The key to the bedroom.
What kind of things might be mechanical?
Oh, you know that camera.
I just thought about that. Yeah, you know.
Matt, can we talk to you outside?
Robots.
Robots in the bathroom?
Roomba, let's go.
Okay. Sure, why not?
Toilet?
You know the really old toilets where you had to pull the string and flush
Yeah,
it?
like remember those old toilets?
They still have those. Calm down, they're still thinking our ideas, right? Oh no, like the lever can be, you know, when you flush the toilet.
Vacuum cleaner?
Because if you click a thing that pops it out, so a vacuum cleaner would have a lever on it.
It has a lever on it. I guess so.
Yeah.
I mean, you don't tend to use the lever for much.
Sure you do.
But-
You use the lever to like make it click on everything. And you're like,
What about a toaster?
Okay.
About a
Oh,
toaster?
sure.
Toaster. Toaster for lever.
What?
Toaster. You know, you're pushing it down and then it kind of pulls the toast down.
Okay, yeah.
And a bagel.
It's a small lever, but yeah.
what's the lever for? For kitchen toaster.
Yeah.
And then for the bedroom, I put a vacuum cleaner.
What? Okay.
Toaster for the bedroom.
Lever vacuum. Oh, we're done with one thing.
The longer the handle, the more mechanical advantage you have.
Bedroom. Which
Is
bedroom?
it a lever or a pulley?
Depends on which part.
Screw.
I just put screws in the garage.
Yeah, the
In the
it's
garage.
pulling on the chain, isn't it?
Literally put screws.
I know.
Pulley?
Gotta put it.
A pulley for the garage. You snap it.
Straight attached to it. So it's not going
We still
around.
go to internet on Thursday?
Isn't that on Thursday?
Yeah.
So yeah, more or less. The chain itself doesn't really give you much mechanical.
Depends on what
It's a
time.
lever.
Oh, you know.
Yeah, that's what I'm saying.
Yeah.
So you can just kick it out and
It's not pulley, it's a lever.
Well, I'm sorry. I didn't say shit.
It's a lever, it's not a pulley.
Then you got like 3 things on
Outside
this.
the garage is good.
Got the mic and 2 cameras right
Well,
now.
the chainsaw be a pulley, pulley can be.
I got one right there too.
Chainsaw?
Yeah, you know what? That is a very simple pulley.
Alright, just start telling the
Would
story.
chainsaw be a pulley? Because we knew.
So there was this one time at band camp.
Oh, I told you.
Alright, so the bathroom. You can plan this thing in the bathroom.
There were 3 little pigs.
Focus here. What is that? Vacuum. Two U's.
2 U's?
Yep. Spelled kind of weird.
Oh!
V-A. No. I mean the spelling. Yeah.
2 U's?
I think it's 2 U's. As opposed to vacuum you don't use. Yeah.
I got those in my garage.
Okay, cool. What else? There was, I think there were some pictures in here of things that were
Anything you use?
What about like an iPhone charger? Is that a screw?
iPhone charger. Well, I don't think you screw in
Yeah, you
the
just
charger, right?
push it in there.
Yeah, you just push it in.
No.
Yeah, it's not really a screw.
Or,
There's you have a picture of something, and here that's that type of machine, but something you haven't written down.
pulley for a pulley on the garage? Got a pulley for a pulley on the garage?
Yeah, I guess so.
What?
Oh, it's a jar. In the kitchen, put jar for screws. Jar.
No, a blender. A blender has more gears.
I guess it does have. It typically has a
Huh?
Gears of
So you
war.
can say either wheel or axle.
Wheel and axle.
I told you about that.
When the blades be wedges.
Bathroom.
Wait. Pulley. Oh, we already got something here. Oh man.
What'd you get? Let me see.
No, we're done one. I got one for a gear in the bathroom.
Oh, I was gonna say a microwave.
There you go.
Wait.
Man.
Yeah, you're getting there.
Okay.
Man, you know how it rotates?
Fill in some more of those.
I
years.
That's why I didn't know what
Other than a chainsaw.
You don't have a fan in your bathroom?
No, but yeah, I know what you mean.
I mean, definitely. How's it going?
I was thinking of like
Never
fully-
opened one up to see if there's
fully
gears in there.
Yeah, right.
There could be.
Garage when you
It
pull
might,
the
or it might just be a
garage
straight
door
motor.
open.
hooked up to
I already got that.
I would say wheel and axle.
Incline plane for a bedroom.
Your actual bed?
Like, no, that doesn't work. Incline planes are like.
All right, want to give you just a few more minutes on this.
Does a bed count for like an incline plane?
A bed for an inclined plane?
Yeah.
Yeah, because we
You have,
sleep
like, your bed on a
slanted.
slant or
Yeah,
something?
we sleep
Oh, I mean,
slanted.
if you're like us and your bed's broken.
But this isn't a hospital.
That
Yeah.
kind of a
But some
bedroom.
people have
Yeah,
hospital beds in their bedroom.
You're stretching it like way out of proportion.
Nick, we're talking to the enemy team right now. Don't even talk to them.
Okay, but are you using it like a machine? Like, are you pushing something up the inclined bed?
What gears are in the bathroom?
I mean, well, technically we are. We're pushing ourselves onto the bed.
Can you use it for that purpose? Okay.
Alright, bed.
Like, not
We got
like
that
a-
bed.
like a gear.
Alright. Bathroom, incline plane. Toilet seat.
Maybe an incline plane can be your shower. Because you know how a shower has to be a little bit slanted
Yeah.
so that the water can drain?
Yeah.
Oh, yes.
Shower.
Even if you don't have it in your kitchen, maybe somebody has some.
That would be the bathtub, right?
Yeah. Or like your shower floor. I will say the shower floor because your shower floor has to